So I'm going to start by asking a question. Raise your hands, everyone. How many of you have ever hit Ctrl-C while running a command line program? All right, that's pretty much all of you. How many of you have ever encountered data corruption because you hit Ctrl-C at the wrong time? That's like most of you as well. All right, so I'm Rain. I use they, them pronouns, and I'm going to be talking about things I've learned about signals from working on Cargo Next Test. So this talk is structured in 3 parts, and part 1 is an introduction to signals. Now, the first question you might ask is, why should you care about signals? Well, if you're a service running somewhere, the life cycle of that service is generally going to involve signals. So this is a screenshot of Kubernetes documentation explaining that when your service is shutting down, you're going to receive this thing called sigterm. And Docker works the same way with Docker stop if you ever want to check that out. You should also care about signals if you're writing command line tools. So the fact of the matter is that most users are really impatient, and they will hit Ctrl-C and send signals to your process if it feels slow at all for any reason. Now, this is a general rule of thumb, but if all you're doing is reading data, then you probably don't need to care too much about signals. But if you're writing data, or especially if you're orchestrating an operation with external dependencies, you really do need to think about what will happen if your user sends you a signal. Now, before we dive deeper, I want to set some boundaries of our discussion. So in this talk, we are going to focus on Unix and not Windows. I'm also going to focus on portable signal handling, which means mechanisms that work on every single Unix. There are alternative ways to handle signals on some Unix platforms. If you've heard of Signal FD on Linux or something like that, they are beyond the scope of this talk. That's a whole rabbit trail that I will not go down. So, all right, so here's a little bit of a crime scene. This was originally a video, but I was told that the conference Wi-Fi might be a little too flaky. So this is a screenshot of me running cargo build and then pressing Ctrl-C in the middle of it. Now, what happened here, right? So the first thing that happened is that I hit Ctrl-C in my terminal. Then the terminal sent a signal by the name of sigint, where int stands for interrupt, to the cargo process. And then this sigint signal caused the cargo process, as well as all the RustC compiler processes underneath that cargo process, to be interrupted and terminated. So we saw the 2 modes of signals here. So one is as a standardized and widely understood way for the kernel to interrupt a process. And then the other mode of signals is as a basic and limited way to perform inter-process communication, or IPC. Now, as a user, you can also join the party of the sending IPCs to processes. So the main way you do that, other than shortcuts, is by using the command called kill. So if you want to send sigint or Ctrl-C to a process, you use kill-int with the process ID. Each signal also happens to have an associated number. And for sigint, the number is always 2. So you can also say kill with -2 and the process ID. If you don't specify a signal, it sends sigterm by default. Sigterm is kind of the generic terminate process signal. And then if you're within a programmatic context, like you're writing a Rust program or a C program, then libc has a kill call, which kill function you can call, which does the same thing. So as I just mentioned, each signal has a name and a number associated with it. If you type in man7 signal on your command line, you will see a long list of signals. So we're not going to go over all of them, so we've already seen sigint and sigterm. Another one is sigkill. Has anyone here ever run kill-9 on a process? All right, so that's all of you. So sigkill is this extra special terminate a process signal. And then I'm sure like pretty much everyone has run into a seg fault at some point. And if a process hits a seg fault, then you actually get this signal called sig-seg-v. Then the last couple of signals here that I wanted to mention are sig-tstp and sig-cont. These signals are used for job control. So if you've ever hit Ctrl-Z in Vim, or FG, or BG, or if you've ever used those commands, then it uses these signals. And if you haven't, by the way, you should check it out, because it's one of the cooler parts of Unix, and it was like an early example of multitasking that is really interesting, I think. So the next thing I want to do is I want to draw your attention to the default action column here. So all signals have a default action, and so some examples of default actions are terminate the process. You can also terminate the process and produce a core dump. Core dump is just basically a snapshot of memory and stuff that you can use to debug a process later. And then also the default action can be to stop or continue the process. Now, almost all signals, with one of the exceptions to sigkill, let you customize the default behavior using what is called a signal handler. And so a signal handler is a custom function that is used to intercept specific signals. With a signal handler, you, as the process, can tell the kernel to call your function rather than follow default behavior. In that sense, a signal handler is a reverse syscall, and sometimes the terminology used for that is an upcall. So, for example, if you're writing or reading data, right, you use a syscall to perform that action. So you use write or read or something like that. In that case, it is you who are driving the process and calling the kernel. With an upcall, instead, the kernel calls your process and your function within it. And importantly, in the case of signals, this can happen at almost any time. And this is where we're going to start running into real issues with signal handling. And this is where the dark corners begin. So to see how, let's walk through a really specific example. For this talk, the example we're going to walk through is a really simple download manager. So hands up if anyone recognizes this. If you were around in the 2000s, then I'm sure, like many people, have used download managers. I grew up with really terrible internet, so these were a lifesaver for me because they could resume downloads and they made downloads faster and so on. So we're going to write a very simple download manager. And so it's really simple, right? So let's say this download tool obtains a bunch of URLs, right? And it maintains their status in a database, downloading them in parallel. So we want to handle Ctrl-C, right? This is a thing that orchestrates an operation which has external dependencies. This is a really good candidate for signal handling. So when a user hits Ctrl-C, we want to cancel any running downloads, flush any data that is in memory to disk, and then also mark the state in the database as interrupted. This seems like a really, really kind of straightforward and sensible set of things that you might want to do in a signal handler. So, your first idea might be, let's just put all of this logic in a signal handler. Can you do that? The answer is no. And why you can't do that is really helpful at illustrating some of the pitfalls of signal handlers. So I mentioned earlier that signal handlers can be called at any time. And this is where this comes back to bite us. So consider what happens if a signal handler is called while you're holding a lock, right? So what happens is trying to acquire the same lock again is going to result in a deadlock. And what that means is that you cannot call functions that try to acquire a lock in a signal handler. Well, which functions acquire locks? Allocating memory requires a lock because it looks at global structures. This means that you cannot allocate memory in a signal handler, which means you cannot construct something as basic as a string in a signal handler. And this shuts off a very large percentage of the things you can do in a signal handler. Now, another thing that can happen is that while one signal handler is running, you can receive a different signal and invoke a second signal handler. And this just makes the system very, very hard to reason about, so much so that in the common weakness enumeration database that is maintained, there are 4 separate CWEs related to signal handling. It's kind of wild. This is the world we live in. It's kind of wild. So if you pull up, so this I know works on Linux. I'm sure it works on some other Unixes as well. But if you type in man7 signal safety, you will get a list of functions described as OK to call in signal handlers. And it is pretty short. Now, one of the things you can do is write to a file descriptor, but you cannot open or seek a file, and you cannot allocate memory. The functions that are OK to call in signal handlers are called async signal safe functions. Now, this term is a little bit confusing because async here has absolutely nothing to do with async Rust. And in many ways, this is actually the opposite of async Rust, because the defining characteristic of async Rust is that you cannot just be interrupted or preempted at any time. You can only be preempted at await points. With signal handlers, you can be preempted at any possible time. So, all right, so how do most modern programs handle signals? To understand that, we briefly need to introduce the concept of self-pipes. So this has been variously described as, quote, a cool Unix hack and cursed on the internet. So many of you are familiar with the idea that you can run a command on a shell, right? So if you run, say, find pipe xargs, which is a thing that a lot of people do, then that creates a pipe. And a pipe is simply a thing that has a read end and a write end. And in this case, the write end is held by find, and the read end is held by xargs. So the idea behind self-pipes is that you can just have both the read end and the write end be held by the same process. And at this point, you might be like, what's the point of that, right? And most of the time, there is no point. Like, this is mostly useless. But it does add value in the specific context of signal handlers. And so the way most modern programs work is that they keep the signal handler really simple, and they start by creating a self-pipe. And then they hand the write end of the pipe to a signal handler and hold on to the read end. And then the signal handler writes to that self-pipe, which is fine to do because a pipe is a file descriptor, and you can read from it somewhere in the rest of your program. Now, I think most C programs do this by hand. But since this is Rust, there's a big crate ecosystem, which is lovely. So you don't have to write this by hand. There are several crates which implement this pattern, and most people just use one of them. All right, so going back to the example, right? We have solved this async signal safe nonsense. We have moved to a world where we don't have to worry about that. You've written to a pipe. How do you handle the read side of the pipe, right? Once you've received a signal, how do you handle it? So one option is we can check whether we received a signal at every iteration of a loop, or maybe every 10th or 1000th or whatever iteration of a loop. And this works fine for small programs that are CPU bound and maybe have like a couple loops. But in my experience, this isn't really scalable to large programs because those tend to have lots of loops, and those tend to be IO bound rather than CPU bound anyway. Another potential solution that some programs use is to basically store all of the state in a mutex and then grab control of the program by locking out all the workers. This is a solution that is used by some programs, but again, in my experience, it is really difficult to coordinate state between the workers and the signal handlers because you have to stash all of the state inside the mutex, and then it just becomes like this whole mess. And I personally really wouldn't recommend following this approach. I mean, if you like lots of mutexes, then more power to you. So I think the most reasonable approach for most programs is to use message passing, where the parts of a program that deal with signals are notified that a signal has occurred. This is possible to do in a synchronous model, but it adds a great deal of complexity because what happens eventually is that you create a nest of threads, and each thread is just passing around these messages to various parts of your program. The good news, though, is that dealing with these sorts of messages is much, much, much simpler with Async Rust. So at this point, you might be like, I'm just a simple downloader tool, Rain. Why would I need async for this? Now, async, the marketing for async has always been for these massively concurrent web or backend servers. A secret, though, is that that is primarily marketing. Its scope is much broader, and it happens to be incredibly well-suited to signal handling with most programs. And the main reason for that is that Async Rust provides these really expressive and powerful ways to perform control flow. So here's a really simple example of Ctrl-C under Async Rust. So Tokyo has signal handling built in. We're going to use Tokyo for the rest of the stock, but this is mostly portable to other runtimes as well. So Tokyo has signal handling built in, which uses the self-pipe trick that I mentioned. So if you want to look at the source code, check it out. Here we are setting up a stream of interrupt or Control-C signals, and then awaiting the method called receive. The receive method resolves each time the process receives Control-C. So this isn't very special by itself, right? You can easily implement this with synchronous code. But this model really shines in more complex code paths because of a neat feature of Async Rust called Tokyo Select. So if you're not familiar with Tokyo Select, it is an incredibly powerful control flow tool that waits for a set of futures to be ready concurrently and resolves as soon as one of them completes. What makes Tokyo Select really special is that it doesn't just work against specific sources of asynchronicity, but against any arbitrary source. So we're going to see it's used with like signals, timers, async functions, you name it. And Tokyo Select is a perfect fit for signal handling. So let's go back to our download manager example. There are a few ways to organize this, but here's one way. So we're going to introduce two constructs that make our life simpler. One is what is called a join set, which stands for a test set of worker tasks that are running in parallel. And then two is a broadcast channel, which allows a single producer to send messages to multiple consumers. And the idea here is that the main task will receive signals and then broadcast messages to workers corresponding to those signals. So we first set up a stream of SIGINT signals exactly as before. And then we spawn a task for each worker on the join set with whatever arguments are necessary for the download, as well as a receiver for those broadcast messages. Now, as far as waiting for values goes, so if we didn't have any signal handling, here's how you do it. So if you just ignore the weird indentation for a second, you'll see that we loop and wait for each worker task to finish until it's all done, and then we handle errors along the way. To handle signals, we use a Tokyo Select with two branches. So the first branch waits for worker tasks to be done, and then the second branch awaits a Control-C message from the stream. And then if it does encounter a Control-C message, then it broadcasts a message over to the workers. So let's start writing our worker function. So we're going to first define our function that takes the arguments that help us download the file, and also takes a receiver for the signal end. So we write our operation within an async block here. And then let's collapse that down to make some space. And so now what we do is we write a loop, and then we use another invocation of Tokyo Select over two possible branches. The first branch drives the operation forward, and the second branch waits for messages received over the broadcast channel. So that is about it as far as basic signal handling goes with Tokyo Select. The biggest thing that distinguishes this model is that unlike synchronous code, it scales up to additional complexity really, really well. So I want to call out two specific examples. So first, you'd likely want to handle other signals like sigterm, since SIGINT is probably not the only signal you're going to receive. And then another common extension is to use what is called a double Control-C pattern. The idea is that the first time the user hits Control-C, you do your regular cleanup as you would expect. But then if the user hits Control-C again, then you can assume that your cleanup process has gotten stuck somehow, and so you exit immediately. So there is a working example of all of this that I've prepared for the stock, and I will provide a link to the repository at the end of the stock. And like these further things are actually done they're not done, and they're exercises for you to do in the demo. All right, so that is about what you need to know if you're managing external dependencies like download files. Where signals in Unix start getting really spicy is if your process spawns other processes. And this is relevant if you're a shell or anything else that spawns processes. And we're going to go deeper into one particular example in part 3. So remember, I'd said in the beginning that when you hit Ctrl-C in the terminal, SIGINT is sent to the process. That wasn't actually quite right. It actually sends the signal to what is called a process group, not just a process. So what's a process group? A process group is simply a group of Unix processes. But it's not just any group. It is a group to which a signal can be sent at once, atomically. And the idea is that the kernel keeps track of that, and you tell the kernel, send a signal to a process group, and then the kernel is responsible for dispatching that signal to all processes within that group. So when you run a command in a shell, it actually always creates a process group for that command. So if you're on Linux, you can print process groups with this command, and you'll get some output that looks something like this. So in this case, the Zish shell created a cargo process numbered 4100. And then when it did that, it also created a corresponding process group with the same number. When cargo build ran RustC, those process groups got inherited, even though the process IDs of each process are different. So if you want to send a signal to a process group, we use the kill command again. So if you want to send signal to a process, you use kill-int with the process number. If you want to send signal to a process group, this is very, very typical for Unix, that you use a negative number. This is just a thing that people do. So you could use kill-int with a negative number. And in this case, SIGINT will be sent to the whole process group. And so that is what really happens when you actually hit Ctrl-C, is that it dispatches this kill-int the entire process group. So, let's say that you spawned a bunch of processes which you think might spawn children of their own. What if you also want to join the party, right? So it seems like a reasonable thing to do, right? Kill off not just your child's processes, but also their grandchildren, and so on. Sounds pretty mysterious. You yourself can create a process group for your sub-processes using this method on command ext. So most of the time, what you're going to do is you're going to pass in -1 for the process group. And what that tells the kernel is that it will create a new process group for you with the same number as the process ID. And that is what shells do. So now you might be wondering, what happens if you have a CLI process and the user hits Ctrl-C? Now, you might assume that process groups form some sort of tree. That in Unix, there is the notion of a parent process and a child process. You might assume that there is a parent process tree, parent process group and a child process group. Well, sadly, that is not actually the case. Process groups do not form a tree. Each process group is effectively its own island. And so what that means is that as this kind of boundary process, which is managing process groups of your own, it is your responsibility to forward signals to child process groups. And the good news, though, is that this is really easy to fit into our Async Rust model, because you can piggyback on the same broadcast channel that you use for signals to also be able to send these sorts of send corresponding signals to the process groups that those workers are responsible for. So it is worth considering the other responsibilities you take up if you do set up process groups. Most programs would want to behave as similarly to the world as possible to the world where they did not set up process groups. And so to achieve that, you'll want to at least forward these signals. We haven't talked much about sig quit, but that is a signal that if you do control and then backslash, then that is similar to sigterm or sigint, except it also does a core dump. There's also sigtstp and sigcont, And those two are actually very, very interesting to handle, because one of the things you might want to do is, let's say you have a process, you're spawning a bunch of processes, and within that you want to be like, you want to time out your processes. So if you handle Ctrl-Z, like sigtstp and sigcon, you can actually pause those timers and then resume them whenever your process wakes up again. And that's a really, really useful thing to do. And it's like a thing that most programs don't do, so users don't actually expect that to happen. But it's a thing that you can do and advertise and so on, and it's pretty neat. It's also worth considering some of the other signals that you'd want to send. Just have like a coherent story for like, okay, here are the things I want to do when I receive a signal. And you do become responsible for more, but you also have like all of this extra ability to deal with processes. So this concludes our brief introduction to the world of Unix signals. And we've barely scratched the surface of the complexity of signals here. I'm going to leave you with a closing thought, which is that Doug McElroy, who is the creator of Unix pipes, wrote in a mailing list post in 2015 that signals were never really designed for IPC. And I think that a lot of what people experience with signal handling and a lot of these deficiencies actually make a lot of sense if you look at it from the, oh, this was never designed to be used that way, and then we had kludge after kludge that was piled up on top of that. And we are living with these original design decisions today, and there are some attempts to solve it in some Unixes, but then those aren't portable. The good news, though, is that with Async Rust, I think a lot of this becomes kind of abstracted away, and all you need to do is write your code in an asynchronous fashion, and and a lot of things become simpler for you. All right, so here is the promised link to a repository containing a working demo of the download manager. There are a bunch of exercises here. They're marked to-do/exercise. Please, if you're interested at all, please try and attempt them, because I think that'll be really illustrative. Here's also my Mastodon, my email, and my blog. Come chat with me after the talk on Mastodon or on the conference Discord. I'll be there in the evening to answer questions there. Thank you so much for listening to my talk. And everyone who's listening virtually, thank you so much as well.